Okay, in this lecture we're going to talk about generalized transition state theory, but to motivate that we're going to talk about some of the limitations of harmonic transition state theory. Now, harmonic transition state theory is wonderful and it's so widely used that I think many people think of it as transition state theory and really equate the two. But many of those same people will tell you that you can't apply transition state theory when you have an ensemble of transition states, that transition state theory cannot be applied when dynamics are important, and sometimes you'll hear that transition state theory cannot be applied when you have fluxional reactants. Okay, so what do I mean by all of these things? Well, transition state theory always works with an ensemble of transition states. Even when we did harmonic transition state theory, the entire collection of states that live on the dividing surface, drawn here in this little diagram, this is the harmonic expansion around a saddle point, and we often think of that saddle point as the transition state. But remember, there's this whole ensemble of them that live on that dividing surface, and every one of them is a transition state. It is an ensemble of transition states. Dynamics are also important in transition state theory, right? Remember how this whole thing worked. We said that this reaction coordinate given by this harmonic approximation construction and diagonalization, we get an unstable mode, and that mode, its dynamics, are separable from all of the others. So it's a very special case, and it conforms very closely to the assumptions of transition state theory, but it's not the only place where we can apply the theory. Okay, so dynamics are important in all reaction rate theories, including the harmonic transition state theory. It's just a very special case. The last bit is that people talk about this fluxional reactance. So what do we mean by that? I mean that you have a large basin of rapidly interconverting species that can all be thought of as reactants that access each other many times before you ever go over the barrier, and together the ensemble of those things makes up the reactant state. So obviously systems that have these characteristics are much more complicated, and they don't conform. What people are talking about, at least, are systems that don't conform to these harmonic approximation assumptions. So let me sketch a little picture of one of these. So this is trying to look through a pass with lots of little basins and little saddles going over that pass like this. So if you were to think about the different ways you can go over this pass, you could cross over here, or here, or here, or here, or even some of these points in between. Okay, so in between, down here, these are the fluxional reactants, and of course the barriers to go from one of these to another are very small compared to the barrier to go up here. And so these things are going to be interconverting very quickly. And I can roughly think of all of this as one big equilibrated basin waiting to find its way over this high pass. Now I have also a whole ensemble of transition states here, and I might be able to imagine coming up with a dividing surface to pass through all of them simultaneously. And if I could, then I would have the ensemble of the entire transition state ensemble corresponding to some special point along my reaction coordinate Q. So to describe problems like this, of course, is much more difficult. For example, you would never try to apply the generalized transition state theory that we're about to learn to a protein folding problem, or to a nucleation problem, or to some complex self-assembly problem. These things are way too rugged in the energy landscape, and the dynamics are not at all like the assumptions of transition state theory. But there are cases that do look kind of like this, where transition state theory can work pretty well. The example that comes to mind are catalysis problems, where you have a homogeneous catalyst, and maybe you have some water molecules that explicitly participate in the reaction coordinate by helping to shuttle protons from one donor to another acceptor. So obviously it doesn't really matter which water molecule does that job, and so you're going to get a whole ensemble of different transition states that are all really equivalent. But the things that are important are the bonds that are being broken and the bonds that are being formed, and because you don't want to tag specific partners as participants in those bonds, you might think about using a collective variable as a reaction coordinate. Over here, we're going to think about collective variables as our reaction coordinates. And over here, we think about this unstable mode. So it's not, the unstable mode itself is not my reaction coordinate. Specifically, my reaction coordinate would be the unstable mode dotted into my displacement from that saddle point. And that would give me a very specific reaction coordinate that's a scalar that tells me how far I am in this direction. So a point here, for example, would have the same reaction coordinate as a point here and the same reaction coordinate as a point here because they all lie along the line that is this far from that dividing surface along that unstable mode direction. Okay, so hopefully this kind of gives you an idea that in harmonic transition state theory, the reaction coordinate that we use is very specifically prescribed. For these problems, we might be using things like coordination numbers. All right, so let's go on now and talk about this generalized transition state theory. In the generalized transition state theory, we're going to build everything around a collective variable reaction coordinate. That could be a bond distance, it could be a difference of two bond distances, it could be a dihedral angle, it could be coordination numbers like I mentioned in the last video. We're going to also define a reactant part of our phase space, and we're going to define a product part of our phase space. These things called indicator functions. All right, so if you're worried about the proliferation of all of these characters in the theory, rest assured they're going to vanish before we get to the final expression. Okay, so the indicator functions just basically tell me that the value of this indicator is 1 if the value of my collective variable, q of x is greater than some threshold that tells me that I'm in the product state. And it's going to tell me that I'm not in state B if q of x is less than q double dagger. Okay? And then we can also devise an indicator for state A that is just going to be 1 minus hb. All right? So these two regions, A and B, are mutually exclusive and they cover all of space. Okay? So let me try and draw a little diagram to illustrate what I'm talking about. So we have some dividing surface in space, and I have a coordinate system that really lives in very high dimensions. Impossible to imagine. This is like 3n-dimensional space here, describing this region. And everything on so this surface that I've drawn here is the surface where q of x is exactly equal to some special value of q that corresponds to my transition state ensemble. And if I'm at a point, so sticking out of q everywhere is an outward unit normal, if you want, that is perpendicular to the surface at this point. Not sure if I'm doing a good job of drawing my axes here. All right, so this is my outward unit normal, and we'll give this a name, and we'll actually use it quite a bit in the theory. So this is the outward unit normal at location x along this surface. All right, and then we can also think about for any point in space that's not on this surface, we can assign it A or B by looking at these indicator functions. So everything on one side of this surface is going to belong to state A. And these are, of course, all the points where q of x, we said, was less than the transition state value. And all the points out here are points that belong to state B, and they are greater than the transition state value. All right, so if they were equal to, they, of course, would be on that surface, and they're not. By the way, we can parameterize this by taking the gradient of our reaction coordinate, which is a function of x, right? Remember that this was a function of where we are in space. So we can take its gradient, and we can normalize that, and it gives us this unit vector pointing on the direction that you would need to go to pass through this dividing surface. And now, the strategy behind the calculation in generalized transition state theory is going to an equilibrium statistical mechanical calculation of the flux passing through this surface in one direction at equilibrium. Okay, so we have our summary of the setup here. This is my diagram depicting the dividing surface in space. The dividing surface is parameterized by the set of points for which my collective variable is equal to the special value that tells me when I'm at the transition state. I have points to the right of that are places where I'm in state B, points to the left of that where I'm in state A, and I have a outward unit normal at every point on this surface that's given by the gradient of my Q function divided by the norm of that gradient. Okay, so remember that the transition state theory rate that we want to compute is the flux at equilibrium in one direction going through the surface. So we're not counting the backward flux because that would exactly cancel and we would get a rate of 0. But we are computing at equilibrium the directed flux that passes through this surface, only counting the flux in one direction. So that's this notation that I've used here. It's an equilibrium average. It's a flux, but it's a directed flux, only counting the flux to the right. And that's going to give us our transition state theory rate. Now to convert that rate into a rate constant, I want to take that flux and divide by the population of my reactant state. Now that may not look obvious to do, but basically what we're going to do is count. We're going to count an average over all the states that live on the left of this diagram, and the way we do that is to average over all the states in the whole space, but what we're averaging is this indicator function that only takes the value of 1 when we're in the correct region. Okay, so the real challenge here is only to compute this flux, this one-directional flux in the space. All right, so let me go ahead and set up that calculation here. So the flux that we have to compute is a rather complicated one, right? So we're going to set this up as a surface integral first, just like you did back when you took physics class. You probably learned about Gauss's law and you did some surface flux integrals. But in those problems you had very nice geometry, cylinders and spheres, and things where you could actually do those calculations. In 3 dimensions with a often complicated expression for the surface that you're working with, it can be much more difficult. Okay, so we're going to need some tricks in order to get by. But let's go ahead and write down the task that's in front of us, and then we'll think about what tricks we're going to need. Okay, so we're going to do a surface integral, and we're going to integrate over the entire surface that's parameterized by this, and I'm going to write my surface area elements as ds. Okay, and of course we have to come up with coordinates to parameterize those. Those would be the 3n minus 1 coordinates that we did not use when we specified the reaction coordinates. So this would be an integral over everyone else, and it has to parameterize this surface. Pretty complicated thing to do. Fortunately, we won't actually have to do it. But this helps us get started. Okay, so what we're integrating is an equilibrium distribution. This is what gives us the equilibrium average here, over coordinates and momenta into 3n dimensions. Velocity of trajectories as they pass through this surface, and we want the component of the velocity that's directed along this outward unit normal, and we only want to count that half of the trajectories that are going this way and not the ones that are going this way. Okay, so the half is going to be accounted for right here, and we're going to take a dot product between r and the velocity along that trajectory x. Okay, so you would get this really by using Hamilton's equations of motion, for example, to write down the time derivative of your vector x in terms of the momenta for that particular to do this horrible integral. Let me just rewrite that. Okay, and so it's the velocity along x dotted into the gradient of q, and then I have to remember that when I change this n into the gradient of q, I have to remember that I need that normalization factor. So I'm going to keep that in there as well. Okay, so I'm just going to write it outside the absolute value. This is always positive, so I can move it in and out of the absolute value sign. Doesn't make any difference. A little bit. And here is q dot. Okay, so this is just q dot. Okay, this is the velocity along my reaction coordinate q. And now we have this surface integral that I'm integrating over a surface parameterized by Q, and at every point on the surface I'm dividing by the length of the gradient of Q, and that suggests something that will be quite useful to us. Okay, so remember in calculus you learned how to integrate delta functions. So you learned that if you have an integral over f of x times delta of x minus x naught, that gives you f of x naught. Okay, that's of course true as long as this integration bound covers the region where the value x naught. As long as that's true, then you'll get f of x naught. Now, a little bit less familiar of a result, perhaps, is that if I take f of x, and I now have an integral over q of x minus q naught, as long as my integration bounds include the root where q of x is equal to q naught, then this ends up being f of x naught divided by, let me write q prime of x evaluated at x naught, and I have an absolute value sign down here. Okay? So if you look at this result, you recognize that this is actually quite similar to what we have here. Okay? So we have this 1 over q prime corresponds to the 1 over the gradient of q here. And the f of x would be all of these other things, my equilibrium distribution, my q dot, all those things are my f. So now this is a multi-dimensional generalization of this second formula down here, okay? And the way we're going to use this in this case is that we're going to replace this awful surface integral with a volume integral. But that's going to come at the cost of having to introduce this delta function in here. Okay, so we have a 1/2. Now we no longer have a specific bounds on our integrals. We're integrating over all 3n dimensions and not just over the 3n minus 1 that live in this surface. So we're integrating over dx and dp, but we're getting back the focus on the surface by including a delta function here. Okay, so this is going to be the definition of our surface. All right, and now the f includes all of the things that we were multiplying, right? That were multiplied by, that were appearing in the integrand in the original surface integral. All right, I think that's everything. So let's just cover again what happened. We had the ds and the 1 over gradient of q that were traded for, and then the thing that they were multiplied by was this q dot and the equilibrium distribution. And so instead of doing it that way, we're now doing a volume integral with a delta function and the same things that they were multiplied by. Okay, so this is now, it turns out that in high dimensions, these kinds of things are much more tractable to work with. All right, so now you recognize that we really have a equilibrium average here on our hands. So this is just 1/2 of the absolute velocity along q times delta of q of x minus q double dagger. Okay, so this says that the flux at equilibrium is 1/2. This is the directed flux, the part that's going to the product state, is 1/2 of the equilibrium average of the velocity along my coordinate q multiplied by a delta function, which tells you whether you're at a particular configuration that lives on that dividing surface. Okay, so this is an unconstrained canonical average of a flux operator. What we now want to do is to write this as a transition state theory rate constant and to make some simplifications to this to make it an easier thing to think about. Okay, so what we do is start by saying that KTST is, and then I have to divide by 2, that was my factor of 1/2, times the average of my indicator function HA. Okay, so this is in principle a complete result, but it's not a very convenient one. What we're going to do instead now is we're going to multiply and divide specifically by delta of Q minus Q double dagger. Okay, so I'm going to multiply and divide by that object, and that's going to give me, I still have my factor of 2 here. I'm going to keep it sitting in this part of the expression, and I have to account also for a average over my my reactant population, and I have to now multiply. All right, so I haven't changed anything. I just rewrote things in a convenient way. Okay, so what is this first thing in this expression? This is of the average absolute velocity along my reaction coordinate constrained over points that live at the transition state. And the second quantity is, by definition, it is the probability to find yourself at the transition state relative to the probability to find yourself in the reactant state. And this is a quantity that we define. All right, I'm going to write e to the minus beta delta f double dagger. Okay, so we are implicitly defining these quantities. So we have the average absolute velocity along our reaction coordinate at the transition state is given by this. All right, and then beta delta f double dagger is defined in the usual way, minus the log of the equilibrium probability to be at the transition state relative to the equilibrium probability to be in the reactant state. Okay, so this is this generalized version of transition state theory, and that naturally comes out of an umbrella sampling calculation, and it gives you some idea of why it took so long for this version of transition state theory to catch on and become useful. Back when Wigner was doing these calculations, he was doing them for and didn't need computational machinery to do the kinds of integrals that he was doing. But now this has since become a very powerful framework for connecting directly to the kinds of things that we compute with rare events methods. Okay, so I've taken my results that we just developed and written them on the left, and summarize again what we have here. So we show that the transition state theory rate constant, according to this generalized formulation, is 1/2 of the absolute average velocity along your reaction coordinate Q at the transition state, multiplied by this e to the minus beta delta f double dagger. This is a Landau free energy barrier, and I will talk about that in just a moment. All right, so I'll refer to this as the rare events formulation of transition state theory in many contexts, because these are exactly the kinds of free energies that come out naturally from things like umbrella sampling or metadynamics or Blue Moon Ensemble MD. Okay, so this is a pretty basic, easy equilibrium constrained average, also something that you can do very easily using rare events methods in computational contexts. Okay, so this is a constrained average. You're averaging this thing in an ensemble that's constrained to this location. So that's what this little notation here with the double dagger next to the equilibrium average means, is that it's an equilibrium average with a... so this free energy barrier is defined in the usual way, minus kBT times the log, in this case the probability of being right in the vicinity of this transition state location relative to the probability of being confined to the reactant state. So this corresponds to a reversible work to take your ensemble of reactants and transform them into an ensemble of transition states. And if you're doing this by an umbrella sampling calculation, then this would be the Landau free energy evaluated at the transition state minus this Landau free energy in this exponential. I've made a mistake here before I wrote this down. kBT times the log of an integral L to the minus 1 e to the minus beta f of q integrated over all of Bayesian A dq, like this. Okay, sorry about that. I had an error in my notes. These Landau free energies, what are they? You have probably seen these before if you took statistical mechanics. People talked about Landau free energies in the context of phase transitions. You have some order parameter q, And that order parameter, for example, for a vapor-liquid transition might be density. For an Ising model, it might be the magnetization. And above the critical point, your Landau free energy profile looks something like this, with only one minimum. And then as you drop down below the critical point, you'll start to, so maybe at the critical point, you get these huge fluctuations because the basin becomes very flat in here. And then below the critical point, you'll get something that looks like this, where you get a system that can break symmetry and split into one of two states. So these profiles were free energies as a function of your variable Q, and you got them by constraining your partition sum to microstates that were consistent with that particular value of the order parameter. So in our case, the order parameter is our reaction coordinate, and we're doing the same thing. We're constraining the partition sum when we compute these things to those microstates that are consistent with a given value of Q. And that's what this delta function is doing, right? It's that constraint to only count those states that are consistent with my value Q dagger. Okay, so are the tools of the trade. And this is not a course about rare events methods, but it's useful to know that this is what they're for. It's for doing calculations for things like this. And we will also use this theoretical framework in some examples, doing calculations that you can do by hand. Of course, it is very useful for those things as well in many contexts.